It's my pleasure to introduce Alex Nugent. He's an inventor and entrepreneur. He has a very interesting journey as to how he came about to running this Gnome Incorporated right now. Or no. As an undergraduate physics major in 2001, Alex invented and patented an electronic device that would later become known as Memristor. So some of you might have, or most of you in the class might have already heard about the Memristor. So he came about with that idea in 2001, with the idea of using it as a synapse and physically adaptive neural hardware. So in the years that followed, Alex has built a theory on how to use memristors in learning circuits called AHaH Computing, which is what we're going to learn today about. And Alex's work inspired the creation of DARPA's Synapse program, a program he helped to create and advise from its inception until 2011, when he left to pursue his own work on thermodynamic RAM, a general-purpose machine learning processor. So Alex is the author of multiple peer-reviewed papers, and he has over 40 US and international patents on memristor neuromorphic system. So just to give an example, like my students come up with an idea and they were looking for, they thought it was the coolest idea and probably they could patent it, and they look up and guess what? Alex would have already done it 10 years back. So, so it's really an honor to have him here. Let's give a warm welcome to him.
Thank you, Dr. K. Okay, introduction to AHaH Computing. The primary goal of AHaH Computing, you always have to know what you're trying to do. And this is what I set out to do, which is to solve the problems that brains solve. I'm not trying to build a brain. Okay? I'm not trying to mimic a brain. I'm just trying to solve the same types of problems that brains solve. There's a whole bunch of people trying to solve these same problems, and there's a lot of different approaches out there. And there's a lot of ways you can divvy them all up. In general, there's two main camps. Okay, there's the machine learning folks, and they're focused on algorithmic or mathematical building blocks. These are very practical people. They are very mathematical people. They use the tools that are available to them, the personal computers, more recently GPUs, and they're searching this mathematical universe, trying to find the building blocks of intelligence and learning systems. There's another group, sort of roughly categorized as the neuromorphic folks. And they say, well, you know, brain is built of neurons, right? This is the building block of a brain, therefore let's figure out how neurons work and how they're connected and the types and all of that. One thing that you find really quickly is that the hardware of a brain is phenomenal. You compare it to modern methods of computing, and they're not even remotely in the same category. What brains can do and the power and space that they do it is unbelievable. And so the neuromorphic folks are like, oh my God, we got to figure that out. And usually they're focused on hardware, which is odd because the machine learning folks just can't stand the thought of hardware for the most part. They just want that to exist to support their mathematics. AHaH Computing focuses on both of those, on both the hardware and the machine learning from more practical aspects, but it comes at it from a different perspective. It focuses on the self-organizational building blocks. And let me explain what I mean by that. Let me go ahead and get the lights here. There you go. Okay, so first of all, what is self-organization? You read up on Wikipedia, and this is what it tells you. A spontaneous process where some form of overall order or coordination arises out of the local interactions between the components of an initially disordered system. So first of all, that sounds a bit like learning to me. Okay, that's one observation. The second one is that the brain is a self-organized system. Nobody built your brain. Your brain built itself. Nobody built you. You built yourself. Okay? Every living thing on this planet and a whole bunch of examples of other things all built themselves. They're all self-organized. Okay? So if a brain is a self-organized system, then maybe let's go look at some other self-organized systems that are simpler, okay? And use those to study. And maybe we can bring something back in understanding the brain. Because the problem is that the brain is crazy complicated. There's so much going on there, right? So that's one big motivation for self-organization. The other one is what I call the adaptive power problem, which is to say, it's what the neuromorphic people understand. You got to look at the physics of learning and adaptation. And you take a close look at that, you go, oh, we need to think a little deeper about the stuff we're doing and how we're going to solve these problems. Okay. So here's some examples of self-organization in nature. On the left, we have a plant. I just want to bring your attention to its structure. Look how it's built. Okay, you see these, I've circled these points of bifurcation, okay, these branches, right? It looks like a tree. This is like a fern. Looks like a lot of things in nature. But you could imagine the structure is basically the repetition of this building block that occurs again and again and again, right? It's this bifurcating point. On the right, I have another example of a self-organized system in nature, a lightning bolt. It looks like a tree upside down, or the roots, right? Again, it's this energy dissipation system, and it's formed of all these bifurcations, and it's spreading out in space, time, okay? And again, think about how you would construct this. What's the building block of this? Okay, and I say it's this point of bifurcation. Now, if you look at nature in general, take a step back, really look at everything that's around you. You'll find that this pattern, this energy dissipating fractal pattern, is everywhere. Okay? Our neurons look like this. Trees look like this, roots, leaves. Our circulatory system, our lungs, mycelial networks of fungus, canyons, rivers, right? Over and over and over again, you see this structure. And in all cases, you can sort of see it as built up of this base pattern again and again. There's always something that's flowing, right? And there's always something as a container that it's flowing through. And if you try to make that simple, what's going on in nature? What's this repeating thing? I say it's energy dissipation pathways competing for conduction resources. This sounds a little disconnected from what I'm showing you, because there's examples that don't look like fractal trees, but you can understand them like this. Like companies, economy is a self-organized system, and it's all formed of these companies competing over a conduction resource, money. There's always these particles that are flowing. In the case of the circulatory system, it's blood and neurons, it's neurotrophins, and in lungs, it's air. Again and again, you see these energy dissipating systems. Now you can build this building block. Okay, and I show this down here at a lot of different ways. And here's one way to do it. And it's a thermodynamic process. And it's all about how this container adapts, or how the conduction resources are competed for via these dissipation pathways. Okay, so there's this building block that creates all of these things we see in nature. And I claim it's a universal adaptive building block. And when you look at how it works, which I'll show you, it has this plasticity associated with it, which I call anti-Hebbian and Hebbian plasticity. Okay, what does this matter, and what in the world does this have to do with computing? Okay, here I am talking about like rivers and arteries and lungs and stuff. Okay, why is this about computing? So let's perform a thought experiment. So thought experiments are usually never intended to actually be done in the real world. It's usually performed as a way to just test your assumptions. Am I thinking about something correctly? What are the implications of it? They have a really nice habit of pissing people off who haven't thought through their assumptions, which I have this nice little raccoon here because he's having a thought experiment. Okay. So let's perform a thought experiment. We've probably all seen plots like this of Moore's Law, right? Made famous by this guy, Ray Kurzweil. And he finds these metrics, in this case, calculations per second per $1,000, and plots them over multiple generations of technology. So on the left, it's like mechanical systems, and then vacuum tubes, and discrete transistors, and then integrated electronics, but first bipolar, then CMOS, and it just has this like steady exponential march up. And so he fits it, and he extrapolates, and you see that that continues pretty soon. In not too many years, we're going to have the ability to buy a computer with the power of a human brain. Okay, so first of all, wow, that would be amazing if we could do that. And second of all, what is it going to take to make something like this. Okay, so will our current methods of computing get us there, or are we going to have something else? Okay. So here's the thought experiment. Let's imagine we want to simulate something between, say, the human brain and all human brains. Let's make it personal. Let's simulate us. Okay. We're going to make this amazing parallel computer, all right, formed of all of these little cubes, all locally connected in 3 dimensions. Forget about how we power it and how we cool it and all that stuff. And we're going to allocate each one of these processors, which contains a CPU and RAM, to one cell of the body. Okay? And we're going to simulate this body. Now, you can simulate at all sorts of resolutions. That's what's wonderful about performing a simulation. So let's pick some numbers. Okay, so how many variables are we going to simulate? Well, on one end, you could have 1. Is the cell alive or is it dead? On the other end, you could be simulating like every molecule and its position, its momentum, like inside the cell. Okay, and so in that case, there's over 1 billion proteins in the average cell. Let's pick 100. Okay, so a neuron in a brain on average is about 1,000 synapses, so this is less than that. How many bits per variable? Modern computers are up to 64 bits. I think that's overkill. Let's scale it down to 32. There's 50 trillion cells, give or take a few, in a body, so we'll take that number. How many updates per second are we going to need? Well, the time scale of cells is about a millisecond, sort of the macro scale. That's the time scale of a neuron. If you're talking about, like, the vibrations of molecules, right, we're up at femtoseconds. Okay, so we're going to pick something in between. Okay, so a gigahertz or a nanosecond update. That's about the time scale of RNA being converted to proteins with ribosomes. And I looked this up and I have a reference. Okay, so now we have all these variables. How much energy is it going to take to communicate this information back and forth between the RAM and the CPU? Okay, back and forth, back and forth, back and forth. Trying to update this quickly. Well, you have to charge a wire in order to communicate. Okay, and so the more capacitance that wire has, the more electrons it soaks up, the more energy it's dissipated. Okay, so a standard rule of thumb, I was taught, but this was a while ago, 0.2 femtofarads per micrometer capacitance in CMOS wire. You could raise that or lower it if you want. Plug all that in, what do you get? Okay, well, if it's 1 volt and the distance is 1 centimeter, which is maybe about modern computers, your simulation would consume 160 terawatts of energy. We're not communicating between the cells, not actually performing the energy of the computation, just shuttling information back and forth between the memory and the processing, internal to each one of these things. Okay? That's over 10 times the global electricity production of the planet. But you say, well, wait a minute, Alex, so we can make these things really small, right? We can. Okay. Let's drop the voltage to 0.025 volts. Okay, that's special because that's KT, that's a thermodynamic limit. That's how much energy an electron accelerated through 0.025 volts is equal to how much energy it has in room temperature. Okay, so we're getting down to the noise level. And we're going to make each of these processors the size of an average cell. Okay, 10 millionths of a meter, teeny tiny. How much energy? 100 megawatts. Okay, that's still 1 million times more than what a body actually dissipates. So does this strike you as odd? Our computers are amazing, but they're not this amazing. All right, what's going on? The answer is very simple, but a lot of people lose sight of this. In brains, all life, absolutely everywhere in nature, except our computers, D is 0. There is no separation between memory and processing. It doesn't occur anywhere except computers. It's a wonderful idea. It's amazing. But it's 0. Okay? We don't expend energy shuttling information back and forth between memory and processing. Okay, so if we want to make very efficient learning adaptive systems, we want to solve this adaptive power problem, how are we going to do it? Well, I think that nature solves it, and I think nature has a universal adaptive building block. I think it's this thing. Okay, adaptation is not computed. You're not shuttling information back and forth. It just happens, right? It's spontaneous. It's self-organized. So let's learn how this thing works, and then let's put it to use. Let's get it to work for us. Okay, so you have to give things names. I wasn't aware of anybody who had a name for this thing, so I call it a gnome. It's this spatial temporal energy dissipating fractal. It's the trees that are growing outside. It's our arteries, it's our veins, it's a neuron, it's a root. It's this thing that you see everywhere that nobody really talks about. Okay? And it's built up of this repeating building block that I call Gnome's synapse. I call it a synapse because this is how I came about it, trying to figure out how to make brains on chips. You could think of it as nature's transistor. Okay? Modern electronic chips, you have this basic building block called the transistor, which you put together in various ways, and you achieve all these useful things. Well, Gnome synapse is apparently what nature has, and it combines it together in all these different ways, and gnomes do all sorts of things. They think, they breathe, they fly, they do all this stuff in nature. Okay? So this is where the memristor comes in, because if we're going to build one of these gnome synapses, we need some kind of adaptive conductive matter. Okay? So our arteries, the thing that's flowing is blood, but the arteries themselves are kind of squishy and they adapt. In a river, water's flowing, but it's flowing over this riverbed. Right? So as the water flows, the riverbed changes, it adapts, it erodes. But we're working with electronics, so we need something that conducts electrons and changes as that flow occurs. So we need an adaptive electrically conductive matter, which is a memristor. Okay? So this guy, Leon Shua, back in 71, I think, he's the first one to mathematically postulate that there's this new fundamental device that should exist called a memristor. And he said famously, if it's pinched, it's a memristor. Okay? So what does that mean? So if you apply, say, a sinusoidal varying voltage across a memristor, and then you look at its current, and you plot those two things, voltage versus current, you get this pinched hysteresis loop. Okay? And what that implies is that this device has memory. It changes its resistance as it's used. If it was just a resistor, it would be a line. Capacitor would be a circle. Okay? And so this is the telltale signature that this is a memristor. Okay? Which is why that symbol on the right, that's the one that I started using out of frustration, because I draw a lot of things by hand. And if you draw memristors over and over again, you realize that the symbol is just, you waste so much time. So that's much easier, and it actually is indicative of a hysteresis loop, which is why I use it. Use it if you like. If you just do everything on the computer, it doesn't matter. So there's all these people, all these universities, all these companies that have shown memristors. But if we want to use them, we have to be able to apply them to our integrated circuits. So what's really useful is something called back end of line. We want to be able to put this on the back end of CMOS electronics, and then we can integrate it and we can make it useful. So you see, if you Google, do an image search for back end of line memristor, there's this woman. Her name is Dr. Chris Campbell, Boise State University. Up in the top left, that's one of her devices. Actually, that second picture there is in my lab with one of her devices. She got her start looking at electron transport and photosynthesis in plants. So she knows how electrons move through things, and so she's able to build the chemistry for these. Okay, so we have to get this building block into circuitry. But it's not really a very difficult building block. It's two competing energy dissipating pathways. Okay, two adaptive energy competing pathways. And so you need a memristor for each pathway. Okay, they're competing with each other, so you need two. When you sit down to work it out, you find that there's actually a lot of ways to do it. Up here you see the 2-1, named because there's two inputs and one output. There's the 1-2 because there's one input and two outputs. There's also a 2-2, two inputs, two outputs, not too difficult. Think of that pair as the synapse itself. Okay? And the difference in conductance between the two is the value of the synapse. Okay, so if one is more conductive than the other, we say that's positive, and vice versa is negative. And the difference is the magnitude of that. So that's really positive, that's really negative, and this is 0. Okay. Now, what happens when you apply voltages to this thing? Okay. This is where AHaH plasticity comes in. So look at that 2-1 circuit there. If you apply voltage to it, let's say it's initially one of these memristors is really positive, the other one is not as positive. Okay. You apply voltage to it, And what you'll find is that if you read out that value, you'll get, say slightly positive voltage. Okay? But the next time you do it, it will have reduced a little bit. Okay? So the difference will go from positive closer to 0, closer to 0. If you started off negative, it'll move it closer and closer. Okay? So if you apply, say, plus V on top, minus V on bottom, and you repeatedly drive this thing, it'll go to 0 volts. Okay? It'll go to 50-50. It'll go to an indeterminate state. Right? Now, if you reward one of these memristors, they're competing for energy dissipation. So if you reward one of them, you can drive the system in the other way, right? So naturally, they're just going to go to 0, but if you give one of them a little burst, you can make it more positive or more negative, whatever you want. Okay, so how do you do this? Well, if you do it in an unsupervised manner, you can imagine that if, say, they started off, one was like this, it was positive. You read it, it brings it a little closer together, but then you reward the one that won. So if it came out positive, then you say, well, I'm going to reward it, and I'm going to make you a little more conductive. Okay, so that's Hebbian learning. So this is anti-Hebbian learning, and that's Hebbian. So if you reinforce the state, you're Hebbian. If you degrade it, you're anti-Hebbian. Anti-Hebbian in this case is passive. You don't have to do anything. Hebbian learning, you have to apply sync. Okay, and you put those both together, you end up with this little Zorro-looking rule, right? Okay, so I'll explain this a little bit later. Important thing to understand here is that this circuit meshes memory and processing together. It's not one or the other distinctly. You access the device, you read it out, but at the same time you're changing it. There's a wait update occurring. Everything is kind of mixed together. Okay, so now we have a bunch of these synapses, you can see here, and we can start to array them together. And you can think of this as a neuron. Okay, so every one of those differential pairs would be like a synapse. And that common node that connects them all together would be like the neuron, a neuron being a collection of synapses. But we can do something pretty tricky, which is we can couple it to random access memory in such a way that we can selectively couple synapses together. Okay? So, to give you an example, we can turn on, say, these synapses here. And by doing that, we're coupling them all together to a common electrode. All the other synapses are decoupled. Okay? And then we can drive a voltage across them, and only those, okay, and allow them to interact according to anti-Hebbian and Hebbian plasticity. Okay? Well, we have an instruction set now, and it's pretty straightforward. Okay? So if we apply a forward voltage, so plus V up here, minus V down here, right, then we have F, that's for forward applied voltage. If we flip it, minus V, plus V, then it's a reverse applied voltage. And then we can do something and drive this sort of node here, which is the output. This is our feedback. If we leave it floating, then that's F for float. If we want to drive these guys high, then that's H. If we want to drive them low, L. If we want to do what I told you before, which is let the system operate unsupervised, and we just wanted to reward the state that it evaluated at, that's U for unsupervised. If we want to do exactly the opposite of that, anti-unsupervised, that's the A, right? And if we wanted to drive 0 volts, then there's a Z, okay? So we have forward instructions, reverse instructions, and you now know what all these mean, okay? This is our instruction set. And you apply them forward, reverse. Why? It keeps everything balanced. It keeps them from saturating one way or another, okay? And you take these cores, this is a thermodynamic core, and you array them all together so you can apply the same instructions or different patterns across all the different cores at the same time, and that's thermodynamic RAM, or KT for short. So why would you want to do this? Well, remember the adaptive power problem. Okay, so let's say you had this simple 3-input neuron. Let's say we separate memory and processing, and we want to compute the synaptic activation, which is the sum over all the synapses, and we wanted to compute some weight update and apply that. So what do? Well, first you have to request the first synapse. You have to bring it in to a register. Then you have to request the second one. Then you have to add them. Request the third one. Then you have to get it back, add those. Then you probably have to go do some other things. And then you compute a weight update. Then you have to request the first one again. Then you have to add those two things together. Then you have to write it back. Then you have to do the same thing for the other one, back and forth, back and forth, back and forth. Okay? Thermodynamic RAM would be different. I want synapse 1, 2, and 3 to interact. Turn them on. Give them the adaptation instruction, get the result back. Okay? The synaptic sum happens for free because currents naturally sum, and the adaptation happens for free because the memristors are adapting as we're using them. Okay? And so it all gets reduced to communication within the chip, and all that other communication, having to read and write memory, goes away. Okay? So you save a lot of time and power. And it's pretty simple, right? It's just all these synaptic things, these Gnome synapses, right? And we're just allowing them to interact in different ways according to this instruction. So what happens when we allow Gnome synapses to interact? Okay, so imagine you're in a dark room, not unlike this, and you see 2 light bulbs, they turn on, okay? And then they turn off, and then one of them turns on, and you're trapped in this room. So you start taking notes. And you see this, all right? So you start drawing them out. Here's bulb 1, here's bulb 2. Sometimes they're on together. Sometimes one of them is on. Sometimes the other's on, okay? So what we're going to do is we're going to take this information and we're going to put it into a thermodynamic core. And we're going to run this unsupervised instruction, FFRU, okay? So forward, float, reverse, unsupervised, okay? So in the case where they're both on, we're going to activate these 2 synapses. All these other synapses we're not using, okay? We just have these 2 here. So in the case where they're both on, we turn them on, we give it this instruction, okay? In this case, where one of them is on, one of them is off, we set that, right? And we give it the instruction. Same thing here. And over and over and over again, we just run this instruction, we load up the pattern. What happens, okay? So this is complicated, but I'll take you through it. Okay, so here's our core, and here is one pattern that's been loaded, and we've executed this unsupervised instruction. Okay, so we can reduce this to roughly a 2-input neuron. Okay, so here's synapse 1, here's synapse 2, input 1, input 2. They're being summed together as a linear neuron does, right? Here we go, x1, w1, x2, w2. We want to solve for that place where the neuron goes from outputting negative to positive, okay, which is a decision boundary. So we set that equal to 0, and we solve for x2, and we end up with this little simple equation, which is the equation of a line, and here's a slope, okay, given by the ratio of these 2 weights. So that's the decision boundary. That's where the node goes from outputting negative to positive. A neuron is this little decision-making thing, and we're finding that place where it changes its mind, okay? So we can draw that, okay? So this is what these lines here represent. First of all, the reason why I'm doing this is because I can plot the data in the same space as the decision boundary, which is a representation of the weights. So I can see how things evolve in time, okay? So if I start off here and I keep on executing this instruction and the data comes in, what will happen is that the decision boundaries will collapse into just a few options. They will descend into attractor points, okay? And that's given here. Here's A, B, C. Now if I plotted this in weight space, synapse 1 versus synapse 2, it would look something like this. So here's all these random initializations, and then I turn on this rule as I give it the data, and it converges to these different attractor states, okay? So here's attractor state A, corresponds to this, call that the null state, and then B and C, which are these guys. Okay, and then here's this plasticity rule again. Okay, so what the heck is going on? What's going on? Well, what's going on is that this unsupervised AHaH rule is doing what's called maximizing the classification margin. Okay? This is a really important concept in machine learning. Support vector machines do all this funny business in front, and then they maximize the support vectors. Okay? This is a solution to generalization versus memorization, which is very important in machine learning. Well, how do you generalize? Well, you maximize the support vectors. Okay, so what's happening here? Here's, say, a decision boundary for the node. Okay? We have data on one side of it. And that data is influencing the decision boundary by trying to push the decision boundary away from it. Okay? That's what Hebbian learning does. But because this funny business where the learning rule is dropping off, the further the decision boundary gets from the data, the less influence it has. So it starts to fall off. But then you start pushing it up against some other data, which falls on the other side, over here. okay, which is pushing back. But as the decision boundary gets close to that, its influence gets greater. So it's able to withstand the influence from the other side. Okay? So the net effect is that the data is pushing the decision boundary around. And the stable point for that decision boundary is a place right in the center that maximizes the margin between the two. Okay? Because the most influence is the data points that are closest to the decision boundary. So it finds that nice dividing point. Okay, this is a very useful place in machine learning. This is where you get generalization. Okay. So you have opposing data distributions fight for classification margin. What's really going on underneath the hood is that you have energy dissipating pathways competing for energy dissipation. Okay. We've made this mapping to this system that does this very useful property. But there's another way to look at these attractor states, which is interesting. They're logic functions. Thermodynamic RAM uses what's called a spike code. And this isn't a normal binary code like we're used to. You don't communicate zero. Zero doesn't exist. Okay? But how do you deal with a two-state system? You have to have two synapses. So if it's a 0, we'll activate one synapse. And if it's a 1, we'll activate the other. Okay? So a two-state system would have two lines, and you'd activate one or the other. Okay, so a 0 goes to this spike pattern right here, and a 1 goes to this spike pattern right here. Okay, so if you wanted to have two inputs, like for a logic function, let's say, we'd map it to a spike pattern like this. Okay, so we can load that spike pattern onto this core. Okay, and again, we don't have to use anything else, just these 4. And then we can execute this FFRU instruction, and we can say what happens. Okay. Well, what happens is that it descends into a attractor state, and that attractor state represents a logic function that is trying to maximize the classification. And if you look at what logic functions you get all of them except for these two here. Anybody know which logic functions those are? Nobody? The XOR function. And you can't get the XOR function if you have a linear system. They're non-linearly separable, or the XOR is non-linearly separable. But you can get it by combining combinations of logic gates in a multi-step process. So what this says is that we now have logic, and we have a computationally complete set of logic functions. We can create whatever ones we want. There's another important concept called independent components. Okay. The information content of natural data streams usually doesn't have anything to do with the amount of wires or channels that data comes over. Okay? So we're almost always trying to represent that data as some kind of building block, some kind of alphabet. Okay? So in vision, you see people trying to extract edge filters. Okay? If you look down low level, you see this common reoccurring building blocks of a data stream. Okay? And then you want to take those edge filters, and you want to combine them together into another layer and more building blocks and so on. Okay? Another way to think of this is, how do you know what the information content is? Well, things that happen at the same time are probably part of the same thing. Okay? So if I'm looking at you, I'm not looking at you. Right? So all the distinct features that come together to represent you only happen when I'm looking at you at that distinct moment in time, and vice versa. Okay? So how do you represent this as a plasticity rule? Well, back in '97, a guy, Riki Oja, he came up with a formalism. Says, well, you can give an objective function for this neuron, and you can derive a plasticity rule. What's the objective? The objective is to minimize pointiness of the distribution. Well, what does that mean? Well, the opposite of really pointy is a bimodal distribution. Okay? And why is that important? Well, because that extracts independent components. Because half the time, the distribution's over here. Things that happen together occur over here, and other moments in time, they occur over here. Okay? So you get a bimodal distribution, you can lock on to independent components. Notice that if you looked at the projection, so this decision boundary right here of this neuron, that's maximizing the margin here, and you projected that, you get a distribution that was bimodal. Okay, half of the features are on one side, half are on the other side. Okay. This is used in something called deep learning recently. It's used to find that factorial code, the alphabet. So, first you extract your letters, then your letters come together to form your words. At every level, you can extract independent components and use those. So here's this interesting, I would say it's more than interesting. This blows my mind, okay? What do you think about it? This really, it gets me crazy excited, and I also think this is a little bit creepy, okay? Here is this building block. This very simple building block, these two energy competing pathways that you see everywhere. I promise the moment you walk outside, you will see this probably 100 million times before you go to bed. Every day, it's everywhere. We're built of it, okay? And we take that, we put it on a chip, and we let these things interact. And what happens? They grow logic functions. They maximize classification margin, which is a very important concept in machine learning. I would say up until about 2008, when everybody just started thinking about deep learning, which is, by the way, independent component analysis, or at least that's a route to it. So there's these three things that happen, very important things, these aren't trivial, that just fall out naturally, no pun intended, from nature's building block. When you allow them to interact, you get all this, all right? So you have memory, that's a given. You get logic, you get machine learning, okay? This is amazing to me. This is crazy. Okay, let's back to reality. So machine learning covers a huge territory, but there's a standard pipeline in machine learning, and it goes like this. You have data of some form or another, and you want to process that, and you want to map it to some number of labels. And the first thing you try is you just take that data and you cram it into some algorithm, and you find that it doesn't work, usually. And then you sit down and you go, okay, well, maybe that's not right. And then you realize, because you probably asked somebody, that really what you have to do is change the data some way first. Okay? So modern, say, convolutional neural networks are the state of the art in image recognition. Well, that convolution is a data representation. They don't just take the image, they do this thing to it. So in the case of this fingerprint, right, you don't just take the pixels of this. You go ask somebody at the FBI, and they go, no, 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 no. What's really important is that there's these ridges that bifurcate, and they terminate, and really that's what you're interested in. And so just look at those and come up with this, this connected, matrix of these dots, and that's what you want to look at. Okay, so we've transformed the data. That's the first step. The next step is something called either feature extraction or learning, where we take that data and then we represent it in various ways. And there's all these different ways you can do it, okay? And the way that is right is the way that works. In this case, you could represent it in lots of different ways. You could say it's the joint combination of all these things occurring together. Well, if you do that, then you might end up with something with a very low false positive rate, but then you might not be able to generalize very well, okay? So you might start breaking up the features a little bit. You'll get more generalization. Your false positive might go down. There's all these different ways, okay? So you create your feature encoding. A lot of the times you do this manually. The big revolution in machine learning right now is to automate this all, is to find some methods like independent component analysis, other unsupervised learning mechanisms for extracting these features, okay? Once you have them, you throw them into a classifier. And that classifier is trying to maximize the margin, okay? That classifier is the final mapping from feature to whatever you need. Okay, so I told you before that thermodynamic RAM takes spike codes. Well, first of all, let me review what a spike code is. People use this word, and it means different things, so let me define it clearly. So that I right there, that would be a spike encoder. It's taking energy of some form or of another and converting it into activation spikes, okay? The total amount, you can visualize this as a bundle of wires, okay? The total number of wires is your spike space. The wires that are hot, that are active, constitute your spike pattern. Spike channel is just one wire, okay? So if you wanted to represent a spike pattern, you just have to list out which spikes within the spike space are active, okay? And if you keep that number low, in other words, it's very sparse, it becomes very efficient, okay? It's just a collection of integers saying spike, 0, 6, 8, 24, so on. So why spikes? The AHaH rule doesn't care about spikes. It doesn't. You can use real valued numbers if you want. All these examples that I show you in nature, where's the spikes, right? Well, I'm looking for a physical solution that I can put on a chip. And if you put analog voltages on it, it works, sort of. But in terms of chip design, moving analog voltages all around the place is actually not a very good idea. There's a reason we have digital computers, right? They're much easier to work with. But it turns out that spikes have all these wonderful properties about them. First of all, they're very efficient if you don't have to communicate too many of them. So if it's sparse, it's efficient. Second, it's a digital code. Collections of integers, right? Those are just binary numbers on a chip. We can do that. It merges very well. Spike codes often generalize better in machine learning. As I told you, it's an important property. They're also much easier to interpret in a lot of context, which I'll show you how that works and why that's interesting. And also, they create very strong and stable AHaH tractor states, which for me is very good. So it all works. From the algorithmic sort of machine learning perspective to the hardware, spikes work great, which is why we use them. OK, let me give you a real-world example. There's a standard machine learning data set called the Adult Census Income. So they sent a questionnaire out to all the adults in America, I think, or a subset. And you fill out all this stuff, right? Your age, your education, your marital status, all this. So the problem is to map all that information to predict one of these variables, which in this case is the income. If the person makes more than 50K, we'll call them rich in a year. If they make less, we'll call them poor. Okay? So how does this work? So we have to convert all of this data into spikes. Okay? So there's different ways to do that, different spike encoders. So think of your eyes, your ears, right, as spike encoders. I'll give you an example of two very simple encoders. So here the number 123. Let's say this is like the oldest person on the census, and that's their age. So we represent a number as a collection, of the 1 in the hundredths place, the 2 in the tens place, the 3 in the ones place. So this, the hundreds, so that's a spike space of 10, and the spike 1 is active. Okay. Here's another collection of wires with spike space of 10, and the 2 is active, and so on. So imagine bundling all that up, you'd have a whole bunch of wires, 30 wires in total, right, where 3 of them are hot or active. In the case of, say, the marital status, let's say there's only 2, I think there's more, married or single, okay? 2 options. So it's a spike space of 2, and one of them is hot, okay? So we bundle all these things together, and we end up with our spike code, which is just a collection of integers, okay? And you can visualize it like this. Now, one interesting thing is that we can now directly index the synapses on KT-RAM. We don't have to do anything. We have this spike stream, and let's say up here, this actually doesn't match, but okay, here are the spikes that are active after our bundle them all up. Well, let's just turn on synapse 0, 6, 24, 34, and 55. Okay. So we turn those on, and now we're going to give it an instruction. So to perform supervised classification, you need this compound instruction. So first you perform a read. In order to get information out of this thing, you can't be driving feedback, so that's why you need the float operation, forward float. Okay. So here we perform a read operation over all the synapses. They're just summing together. Okay. And down here, we do things depending on the output and whether we're teaching it or not. Okay, we give it a different instruction. And if you want to go over this later, let me know. Okay. We have 1 core assigned per label. Okay, so we have a core for rich, we have a core for poor. Okay, and we perform these instructions. And the voltage that comes out during the read operation is a measure of how confident this core thinks that it's its label. So if it's the core assigned to the label rich and it comes out very positive voltage, then it's confident that this is indeed a rich person. Okay. Now we can measure this, and we find that this is benchmarks along with all these other nice machine learning algorithms. So it's useful, which is good for me. Okay, so like I said, each core is assigned to a label, and we can do as many as we want, up to the size of KT-RAM. And they all can be loaded, the same spike pattern can be loaded on each one of them, and they can be executing these instructions in parallel. Okay, so I mentioned that spikes are much easier to interpret. So if you go from some input variable like age, and then you put it through an encoder, you get some spike stream out that exists in a spike space, which all gets bundled up, and it could go through other layers of processing and feature learning, which we're not going to talk about. And then it ends up activating this core, right? And so it learns. So later we can come back and we can read out the value of all those synapses, okay? So we can do an FFRF, so forward float, reverse float. This is as close to a non-destructive read operation as you'll be able to get in thermodynamic RAM, okay? And you can sort the values out, and you can say, what are the labels, what are the spikes, or the channels that are most positive for the label rich? And then you can go backwards. You have these spike encoders. You can say, well, spike 6 maps to education encoder, and that in turn maps to this age range, right? You can go backwards. And so you can read this thing out after it's learned. And what do you see? Well, rich means you probably have a doctorate, professional school or master's. You work 60 hours a week, which is crazy. You're about 50 years old. That's interesting. That's like, you're not retired yet, but you probably worked your way up the ladder. You've been at this for like 30 years. You're in an executive managerial position, right? Self-employed, incorporated. You could own business, right? Makes sense. What about poor? Well, education, 7th, 8th, 1st, 4th, 9th. Okay, you have less than a high school level education. You work for the state government instead of the federal government. You're 80 or you're 20, so you're either really young or you're really old. Okay, so you're not working yet. Okay, so this is interesting, right? Your household cleaner, right? This thermodynamic core operating on nature's transistor was given all these spikes, and it created the concept of what is rich and what is poor. That's the essence of machine learning. Okay? But we can go backwards because we can discretize this into these spikes, and we can trace it back, and we know what it means, right? Which is interesting. So if we have somebody that has a doctorate level education and is about age 50, then we know that this thing is going to say it's probably rich. There's a lot of stuff you can do with the standard pipeline. Okay? So machine learning, again, data, representation, feature extraction, classification. So we can do signal prediction, right? Where the representation is just, we spike encode the past of the signal, and we use it to predict the present. And then if we can take that prediction, feed it back in and on itself, we can recurse it forward in time and make a prediction as far off as we want. Or we could take, say, the joint actuations from a robotic arm, and maybe the distance between the guy's eyes and the ball. And we could bundle that all up into a spike code, and then we could have a bunch of classifiers, one for each degree of freedom of that robotic arm. And then we can get this thing to learn on its own how to catch a ball. It's pretty cool. If we can make predictions and we have a measure of confidence, then we can extract anomaly signals from it. So if you learn a signal, or this thing learns a signal, and all of a sudden the confidence starts dropping, something's up, something's changed. Don't know what's changed, but you can generate an anomaly signal. Okay? And all of this is just the same pipeline over and over and over again. Okay? So I mentioned that, Gnome is a spatial temporal structure. Okay? The time part is really important. And lightning is this phenomenal example of it. And you need to go on the internet and search for lightning in slow motion. Whenever I saw this, I was just transfixed for all sorts of, my God. Right? This is energy trying to dissipate itself, bifurcating, searching for ground. Bam, it finds it, gets it. Okay? So it's not too surprising that we can co-opt this building block in order to solve search problems, combinatorial optimization problems, puzzle solving problems. So Sudoku is an example. You have all these configurations and you're trying to find out what the best configuration is traveling salesman problem. In this case down here, we've directly mapped this process. And so you can see the solution emerging, growing out from this. So far, we found 5 different ways to do combinatorial optimization with thermodynamic RAM. It's fun. So let me wrap it up. Nature has a universal adaptive building block. Did you know that? I didn't know that. I had no idea. It took me like 10 years of trying to build this stuff. And then it dawned on me that this thing that I'd been working with is everywhere in nature. And that nature is built of this repeating building block that creates these fractals. I was blind to it. When I finally saw that, it kind of blew my mind for like a month. Okay, it's still blowing my mind. Okay. Call it Gnome synapse, or nature's transistor, or whatever you want, the oogly boogly monster, it doesn't matter, right? It's just, it matters that you see this thing, because it's everywhere. And it's useful. Nature uses it. Okay? And whenever you let this building block interact, it solves the problems that brains solve. How cool is that, right? Universal logic, perception, planning, control, okay, all this. In terms of perception, we've skipped 2 things here that we've also figured out how to do with thermodynamic RAM. One is feature learning. I mentioned independent component analysis. That's one method of feature learning. Another one is adaptive spike encoding. I showed you how to turn, say, integers into spikes, but you can also do it in an adaptive way, okay? And you can learn that process. And with memristors, because they're adaptive conduits, we can build Gnome synapses, and we can empower our computers, and we can give them access to this intrinsically adaptive learning circuit, okay? And this is important because we don't have to communicate so much anymore. We can make adaptation intrinsic to the chip. We don't have to compute it. And so long as we can show that it actually solves problems well, then we have something that's useful, okay? So I think the future is going to be tremendously fun. And this is what Gnome Incorporated is trying to do. We're trying to make thermodynamic RAM. We're partnered with wonderful people like your professor. And Chris Campbell, who I showed, makes these memristors, right? And we're trying to make this core, this thermodynamic core. So with that, open it up to questions, if anybody has some. Hello, everybody. I'm Alex Nugent, inventor of AHaH Computing. I hope you enjoyed my presentation at RIT. You know, one of our primary goals is to make this technology as accessible as we can. So I encourage you to visit our website, where you'll be able to read lots of articles and find links to various information sources. If you have any questions, drop us a line, shoot us an email, or leave a comment. And if you have any ideas, we'd love to hear them. It's collaborations with people like you that move this technology forward.